In earlier videos, I covered some fundamental skills in statistical data analysis using SPSS, including defining variables in SPSS, screening and cleaning data, and addressing non-normal distributions. Now, it's time to proceed and acquire the skills for conducting statistical tests. To begin, we'll explore nonparametric tests, which operate without making assumptions about data distribution and are suitable for ordinal or nominal data. Don't forget to subscribe to our channel and click the bell icon to receive notifications when we release new videos. Thank you for your support. In the fields of medical and healthcare sciences, certain experiments seek to determine the influence of one binomial categorical variable on another binomial variable. For example, imagine a situation where rats suffering from viral infection X are randomly assigned to either the experimental group receiving drug Y or the placebo group. The aim is to compare the number of rats in the experimental and placebo groups for which the previous diagnosis of X infection no longer applies by the end of the treatment period. In these cases, if the sample size is large enough, one can employ a chi-squared test. However, the significance value it provides is merely an approximation. This is because the sampling distribution of the calculated test statistic only approximates the theoretical chi-squared distribution. The accuracy of this approximation diminishes when dealing with small sample sizes or very unequally distributed frequencies across table cells, resulting in expected values for each cell being low. A general guideline for determining the adequacy of the chi-squared approximation is that the test is not suitable when the expected values in any cell of a contingency table fall below 5, or below 10 when there is only 1 degree of freedom. Indeed, in cases involving small, sparse, or unbalanced data, the exact and asymptotic p-values may exhibit significant disparities, potentially resulting in opposite conclusions regarding the hypothesis under consideration. In contrast, the Fisher exact test, true to its name, is exact as long as the experimental design keeps the marginal totals fixed for both rows and columns, and it can therefore be used irrespective of the sample characteristics. However, the Fisher exact test becomes challenging to compute with large samples or well-balanced tables. Fortunately, these are precisely the conditions where the chi-squared test is applicable. When performing manual calculations, the test is only practical for a 2x2 contingency table. However, the underlying principle of the test can be expanded to apply to the general case of an m×n contingency table. When marginal totals for a 2x2 contingency table are known, only one cell retains the possibility of random variability. This occurs because once the value of one cell is determined, the values of the other cells are automatically fixed. Consequently, it is said that the degree of freedom is 1, for a 2x2 contingency tables. Please note that the Fisher exact test is not appropriate for binary or multi-category variables obtained through stratification or matching. These variables are referred to as stratified categorical data. For instance, when you stratify participants into high anxiety versus low anxiety groups and aim to compare the incidence of high or low blood pressure between those two groups. In such cases, the Cochran-Mantel-Hensel test must be used instead of Fisher's test. Example 1. The outcomes of administering drug Y compared to a placebo on 16 rats, all previously diagnosed with infection X before the study, and randomly assigned to either experimental or placebo groups, resulted in the following 2x2 contingency table at the end of the study. To calculate the expected values for each cell, I multiply the marginal total of first column by the marginal total of first row and then divide the resulting value by n, and then repeat the same calculations for the second column and the second row. Consequently, the expected value for the cells in the first row becomes 3.5, and for the cells in the second row, it becomes 4.5. Example 2. In a study, the association between academic disciplines and smoking was explored. The findings are displayed in a 2x3 contingency table below. I have already computed the expected values for each of the cells and have written them in the respective cells. As it can be seen, all the expected values exceed 5. In such instances, the chi-square approximation test yields acceptable results. However, we can still consider using Fisher's exact test. Now, let's examine how the Fisher exact test is executed for both example 1 and example 2 using SPSS. Example 1, running the Fisher's exact test. Open the SPSS data file for the example 1. Go to the Analyze menu. Select Descriptive Statistics and then choose Crosstabs. In the Crosstabs dialog box, move the Diagnosis into the rows and the Treatment into the columns boxes. Click on Statistics and in Crosstabs Statistics dialog box, select the chi-square checkbox. Then, proceed by clicking Continue. Click OK to run the analysis. Interpreting the results. SPSS will generate the results in the form of a contingency table displaying observed frequencies, along with a chi-square tests table that presents the outcomes for various tests, including Fisher's exact test. Evaluating the statistical significance. Assess the p-value acquired from the Fisher's exact test, located under the column titled Exact Sig two-sided. It's also worth to note that in cases where there's a strong rationale for testing a one-sided null hypothesis, you may also examine the one-sided significance column, to ascertain statistical significance. One-sided tests enhance the statistical power of the test. As evident here, the p-value is lower than the selected significance level of 0.05. Therefore, I infer that the counts of rats with negative diagnoses at the end of the treatment are significantly higher in the experimental group compared to the placebo group. Running the Fisher's exact test for the example 2. Open the SPSS data file for the example 2. Go to the Analyze menu. Select Descriptive Statistics and then choose Crosstabs. In the Crosstabs dialog box, move the Smoking into the rows and the Academic Disciplines into the columns boxes. Click on Statistics and in the Crosstabs Statistics dialog box, select the chi-square checkbox. Then, proceed by clicking Continue. Click on Exact and in the Exact Tests dialog box, select the checkbox of Exact to place the bullet in it. Please note that for 2x3 contingency tables, if you desire the results of the Fisher exact test to be included in the output file, you must click the exact checkbox here. However, when dealing with a 2x2 contingency table like the previous example, SPSS automatically presents Fisher's exact test results without the need to check the exact checkbox. Proceed by clicking Continue. Click OK to run the analysis. Interpreting the results. From the chi-square tests table, it's evident that the p-value of Fisher's exact test exceeds the 0.05 level. Therefore, I conclude that the academic discipline does not exert a statistically significant effect on the number of people who smoke. Exercise 4. I have put the download link of the SPSS data files that I used in this video below in the description. Please download these 2 files and practice all the skills I taught in this video to enhance your learning experience. Please note that the spoken presentation in the current video is created using AI text-to-speech technology. I hope you found this tutorial helpful. In upcoming videos, we will offer tutorials on various other nonparametric tests. Please stay tuned for our next releases.